Okay, before we get started today, a few little announcements. I don't know if you noticed, but we have an exam coming up a week from today. And so we're going to have one last assignment, and it will be a programming assignment, which is due, is it Tuesday? Or Monday? Yeah, Tuesday. But I think what I would like to do today is give you enough information to actually be able to do the homework over the weekend. So we're going to move a little rapidly today, just so that you can have this information under your belt for your homework. Okay, so today's topic, now we have finished chapter 3, in which we have developed some tools for analyzing algorithms and proving correctness. And so that's going to like end the written part of this little season, and now we're getting back to programming. And so in chapter 4, what we're going to learn are some comparison sort algorithms. Now here again, a lot of this stuff should be reviewed. In fact, I think you guys even do the merit sort taxonomy, do you not? Yeah, so good. So the concept, so we'll go pretty rapidly. So the concept will be the same, but there is one thing that we are going to do differently. Now, do you guys remember this book? Yeah. Design Patterns, Elements of Reusable Object-Oriented Software. Okay, remember how many authors? 4. Yeah, the Gang of 4, GOF. Gamma is the first author, so this is the Gamma book. And this is an example. What we're going to do today when we do the merit sort taxonomy is we are going to use a particular object-oriented design pattern. What are the 3 goals of this course? What was the first one? Data structures, C++ programming, and object-oriented design patterns. And so this one, now what we're going to concentrate on is a particular object-oriented design pattern to implement the merit sort taxonomy for sorting. So the topic is comparison sort. So the topic is comparison sort algorithms, and we are going to use a particular taxonomy that was developed by Susan Merritt. And I think I have her original paper. I know I have the original paper on the course website if you would like to refer to that. So in figure 4.1 is a general diagram of the merit sort taxonomy. All comparison sorts, pairwise comparison sorts, can be classified according to this taxonomy. And what we have in figure 4.1 is the general taxonomy. So capital L at the top represents an arbitrary list. And then the way sorting works is you split the list into 2 sublists. So on the left, L1 is one sublist, and L2 is the other sublist. And then what you do is you recursively sort each one of those sublists. So L1 prime is L1 sorted, and L2 prime is L2 sorted. And then you join these 2 lists together, and then L prime is the join of L1 prime and L2 prime. Are you with me? So that's the general way that these sorts are performed. And then what happens is a particular sort, the different sort algorithms differ in the way that they split and the way that they join. But they all do split, sort the one, sort the other, and then join. They all do that, but they differ in how they split and how they join. So part A of figure 4.2 shows how the merge sort algorithm works. So let's suppose the original list is the element 731628854. Now what does it look like the split how does the split happen with this one? What's this? What's on the left? It's just the left half, right? It's just 7316. And then the right half is 2854. So that the split is real easy. All you do is you just say, I'll just take the midpoint, and these over here will be one side. That's all split, the left half and the right half. And then what happens is you recursively sort those lists. So if you sort 7316, that sorted list is 1367, and if you recursively sort 2854, that sorted list is 2458. And so now, assuming that each one of those sublists are sorted, how does the merge sort work? It joins them. Now, how is it gonna be harder to join, or was it harder to split? It's going to be harder to join because it's going to take a loop. You see that? It's going to take, you're going to have to, but it's not going to take a loop to split it. All you have to do is just calculate the midpoint. And so actually your homework assignment for Tuesday is going to be to do the join of the merge sort. And you've probably done this before, I would think, but we will review that. So we want to get to that point at the end of the lecture today. And then in part B of the figure shows the quicksort algorithm. Now with the quicksort algorithm, it's a little more complicated to split, but it's very easy to join. Look at the split. If the original list is 7316284, what happens is it splits it in such a way that each of those numbers in the list on the left is what compared to each one of the numbers in the list on the right? Smaller. So it has a way of getting all the smaller ones on the left and all the larger ones on the right. You see? And then if you recursively sort those lists, what you're going to get on the left is 1, 2, 3, 4, and on the right is 5, 6, 7, 8. So now, because all the ones on the left are smaller than the ones on the right, and if they're sorted, what? It joins easy. It's just automatic. So quick sort is hard to split, easy to join. And then there are two other scenarios where you split, instead of splitting it in half, you just split off one element. So basically what happens is, in figure 4.3a is the insertion sort algorithm. And take a look at the split. Is the split easy or is the split hard? If the original list is 7316284, how does the split happen? It's just the last one, right? And then the remainder is 7316285. And if you recursively sort that, you get 1, 2, 3, 5, 6, 7, 8. But then what do you have to do with the join? You have to put it in where it goes. In other words, you have to do what with it? You have to insert it. You have to insert it. That's why it's called the insertion sort, because in the join you have to insert it. And does that take a loop, yes or no, to do the insertion? It does. What about the split? Does that take a loop? No. And then the other, in part B of figure 4.3, we have the selection sort algorithm. So now with the selection sort algorithm, what do we do? If we have the list 7316284, what did we do for the split? We had to find the what? The largest element. In fact, then what did we do? Largest last. Okay. So we have, and does that take a loop, yes or no? Yes. Yes, it does. All right. And then if we recursively sort 7316245, that we get 1, 2, 3, 4, 5, 6, 7, and then the joint is trivial because it's already the largest last. All right. Now these I think you have seen, but here's another one. We're going to do a fifth one in this class. And this fifth one is called a heap sort. You may not have seen this one, but it's quite common and it has some nice features. Let me state now that the word heap has two very different meanings in computer science. The word heap can mean two totally unrelated things. First of all, you've heard the word heap before. We've used it. Memory. Yeah, it's memory. It's when you allocate storage from the heap. That heap has nothing to do with this data structure heap. Okay, so just keep that in mind. So you just have to know by the context which heap we're talking about. Now we are talking about a data structure heap. All right. Now a data structure heap is a binary tree. And it has two characteristics. It has to have a max heap shape, and it has to have a max heap order. Now, I don't have a sequence of figures in the book that illustrate a max heap shape, so I'm going to do it on the board here. All right? So, because it's kind of hard, it's actually kind of hard to explain. You'll see why. Now, watch this. This tree, with just one element in it, has a max heap shape. This tree, this binary tree has a max heap shape. This binary tree has a max heap shape. Now watch this. This binary tree has a max heap shape. This binary tree has a max heap shape. This binary tree does not have a max heap shape because it wasn't constructed going top, down, left, right. Do you see what we're saying? So on the other hand, this one does have a max heap shape. You see? And can you tell me if this has a max heap shape?
It doesn't.
No, this does not have a max heap shape. Because now, does this have a max heap shape?
No.
No. Does this have a max heap shape?
Yes.
Yes. So you see there can't be any gaps. If you go from the top, if you go top, down, left, right, they have to all be occupied with no gaps. That's what a max heap that's what a max heap shape is. Does everybody see? So it's kind of hard to explain, but you get the idea. Yeah.
So if you had erased one of them and like it was not,
Now if I erase this one, it still has a max heap shape. But if I erase this one, it doesn't, because there's a gap here. Because see, it's boom, 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 nothing, boom.
But at that point, is it even called a heap anymore?
No, it's not. It's not. Because a heap has to have a max heap shape, and it has to have a max heap order. Yeah.
What if you got rid of the right one on the second level?
On this one?
Yeah.
Not a max heap shape, because boom, 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 boop.
Okay.
That kills it right there. So it has to be filled top, down, left to right. Is everybody clear on that? Yeah, question?
Sorry, one more. If you got rid of that, the third node at the very bottom level,
This one?
yeah, that would still be max heap, right?
This is not, because of these gaps here and here. See, look, boom, 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 boom. This is missing, but this one's here.
Okay.
See, look, it's like this. It's like 0, 1, 2, 3, 4, 5, 6.
So those two would still...
So, yeah, there's not a, this tree right here is not a max heap shape. Does not have the max heap shape.
All right. Thank you.
Is everybody clear on that? Okay, so that's the max heap shape. Now, the max heap order is defined like this. For every node other than the root, the value of the node is at most the value of its parent. For every node other than the root, the value of the node is at most the value of its parent. So here in figure 4.4a is a picture of a binary tree. Now, let me ask you, well, it's answers up there. Let me ask you a question. Does it have the max heap shape, yes or no? It does, because see, you see how it's filled top, down, left to right. Okay, but now look, in order for it to have the max heap order, what has to happen is, you see that the root 7 is greater than or equal to 3 and 1. 7 is greater than or equal to 3, 7 is greater than or equal to 1. So that's good. Now let's take a look at the 3. Is 3 greater than or equal to 6, and is 3 greater than or equal to 2? No, so that violates the max heap order criterion. Does everybody see? And what about the 1? That's also bad, because 1 is not greater than or equal to 8, and it's not greater than or equal to 5. Now the 6 is a good one, because 6 is greater than or equal to 4. But it has to be that, it has to have that property for all the nodes. Is everybody clear on this? Yeah.
Does it have anything, does it matter which order?
That's a very good question. Does it matter which, about left child or right child? And the answer is no.
Okay.
Yeah, it only, you see, it's the left child and the right child don't have to have any particular order at all. Yeah, that's a really good question. Okay. Does everybody see that? It's the left child, right child they don't matter. is all that matters is their values relative to their parent.
Okay.
And the parent has to be greater than or equal to each one. Is everybody clear? Now, also in figure A, you see why it's important for this data structure to have a max heap shape. Because if it does have a max heap shape, how can we store it? We can store it in a what? What's the picture? In an array. Now do you see why? And you see why there can be no gaps? Because it makes it convenient, because we can just store it in an array. Is everybody clear? And so what happens is the top element is the first element of the array. The root of the heap is at the first element of the array. Then its left child and right child are the second and third. So you see it's 7, look, 7, just count down. 7, 3, 1, 6, 2, 8, 5, 4. So 7, 3, 1, 6, 2, 8, 5, 4. So what we're going to do is all of these, the heap sort is working on arrays. But we think about their properties in terms of the heap. Yeah.
Do you always assume just two children?
Yes, this is binary tree.
Okay.
Binary tree, which means yes, 2 children. A left child and a right child. They are distinct, a left child and a right child. Okay, so now here's the thing. With this heap sort, we're going to see how this algorithm works after, in a week or two. So we're not going to get into the details of how this happens, but here's what happens. What happens is in the heap sort, with the heap sort, what happens is there is an initial operation that's called build heap. Okay? And figure 4.4b shows list L after build heap executes. And what it does is it makes a heap out of it. So now look at in B. The root is 8. Is 8 greater than or equal to 6 and 8 greater than or equal to 7?
Yes.
Yes. Is 6 greater than or equal to 4 and 6 greater than or equal to 2? Yes. Yeah. And is 7 greater than or equal to 1 and 7 greater than or equal to 5? Yes. And is 4 greater than or equal to 3? Yes. So does everybody see how you can determine now that that is a heap? Because it has a heap shape and a heap order. And so now the way the heap sort works is, take a look at, I've reproduced part B of figure 4.4 on the left here. What do you know if the root is greater than or equal to each one of its children, but then each one of each child is greater than or equal to its children, all the way down, all the way down? What do you know about the root? It's the what? It's the max. In fact, these are called max heaps. You can also define a min heap the other way around. All right? So it's the max. So basically, what have we done? When you do build heap, what have you done? We have done what? We have, starts with an S. Well, no, this is not sorted. Notice we have done what?
Selected.
We have selected the largest one. Does everybody see? We have selected the largest one. So once we select the largest one, we know where that goes. So where does that 8 belong? In the final sorted list, where does it belong? At the last. So what we do is we put it to the last. We make it last, and then we put the 3. We do an adjustment. And then we know that this is that the last element now is in the right place. And so now we consider and then we heapify the data structure. So 7 is greater than or equal to 6 and 5. 6 is greater than or equal to 4 and 2. 5 is greater than or equal to 1 and 3. And we continue that process on down.
But so when it took away the 8, it moved the 7 up?
Yeah, and there is and see, when we look at the heap sort algorithm, we will investigate that in detail. I'm just showing you what happens, not how it happens.
Okay.
Yeah. So this is just where it fits in the classification. In fact, and so here is the merit sort taxonomy. This is how it fits into the merit sort taxonomy. It is basically a what sort. It's a variation of what sort. Yes, it's a variation of the selection sort. So we have an initial operation called build heap that gets it into a heap. We split off the 8, then the 8 is already sorted, and then we recursively sort using the heap sort algorithm 765421 to 1234567, and then we join it. So that's just the concept. So now we're going to start looking at some code to implement this merit sort taxonomy. And this, I think, is different from what you had done before. Now, you know how we just got through saying a minute ago that there are two very different meanings of the word heap? There are also two very different meanings for the word template. Because we have seen C++ templates, right? What is the idea of a C++ template? It's that you design your data structure for an arbitrary type, and then the user of the data structure supplies the type, like double or int. That has nothing to do with the template method pattern, which is an object-oriented design pattern. Now, the template method pattern is one of the patterns in the Gamma book. All right, and so we are in this course we are going to present these object-oriented design patterns the way that they are cataloged in this book, and so we're going to use their terminology, the template method pattern. And this is a great book. It's not required for the course, but you might want to have it if you're going to be doing software development in the future. He divides it into creational patterns, structural patterns, and behavioral patterns, and has one chapter on each object-oriented design pattern, and this is one of them. So, what is the purpose of the template method pattern? Now that we've seen the merit sort taxonomy, we can see how it's going to fit with this. Look, the template method pattern is used when a system must implement an algorithm with an invariant part, which always executes the same way, but which depends on variant parts that are implemented differently depending on the circumstance. Now look, you guys, what did we just see in the merit sort taxonomy? We saw that. What did we see?
The top is always the highest value.
Well, no. That well.
Does it differently?
Yeah. What's the same and what's yeah? What did we see? Yeah, we saw that all algorithms do what? Split, recursively sort, and join. They all do that. Do you see what I mean? How did they differ? In the way they did what? How did they differ? They all, in the way they do what?
Split and merge.
Yeah, the way they do split and join. That's how they differ. But they all, do you see what we're saying? And do you see how this, do you see how this fits? Used when a system must implement an algorithm with an invariant part which always executes the same way. All right? But which depends on variant parts that are implemented differently depending on the circumstance. So, there's two, and here again we're using the terminology of the Gamma book. There are two kinds of methods in the template method pattern. The first one is called the template method, and the second one is called the primitive operations. So in our situation, the template method is the one that is the same. So what is the template method going to be? It's going to be what? It's going to be split, recursively sort, join. Because that, and so look, you guys, we're only going to have to write that code once. Because they all do the same thing, so we only write it once. No duplicate code. Elements of reusable object-oriented software. Only write that code once. And then if we want to do a merge sort, well, we'll do the split and the join for the merge sort. If we want to do a quick sort, we'll do the merge and the join. We'll do the split and the join of the quick sort, etc. All right. So now here in Figure 4.6 is how we implement this. Is the UML diagram for our software architecture for implementing this template method pattern. Now here's the thing, you guys. What is that big, the T and the dash up on the right? That's template, but that's what kind of template? That's a C++ template, okay, which is different from the template method pattern. So we're using templates. Okay, does everybody see what's going on? We're using C++ templates within the template method pattern, but those are two different uses of the words template. So what do you suppose A sorter stands for? Abstract sorter. So we have an abstract sorter, and what operations do we have in this abstract sorter? Sort, split, and join. And do you remember what we said about the font being slanted and font not being slanted?
Not defined there. It's abstract.
Abstract. And so which ones are abstract?
The split.
The split and the join. But which one's concrete? The sort. Because why? Because we're going to actually do that in a sorter. Because that's the same for everybody. Do you see? Are you with me, sports fans? Okay? Because that's the same. That happens the same. So we have, so what's going to happen is, for example, merge sorter is one of these sorting algorithms that inherits from a sorter, and it's going to implement its own split and join, but it's going to use the code won't even be in there to do the sort because the sort is implemented in a sorter. So it doesn't have to be in there. Does everybody see how that works? And it has a little now do you guys remember when you did the merge sorter why you needed a temporary array? Do you remember that from last time? Remember what did you do? How did that, I know you did this. Do you remember why you needed that temporary array? I mean, did you do it recursively?
Yes.
The merge sort? Yeah, I think you did probably.
Yes.
You did it recursively. And do you remember what you have to do? How you merge? Because if you have half like this and half like this, and you put them in.
Then you like put them in the new one.
You put them in, and then you got to copy it back.
Yes.
All right. So this underscore temp A array T is that temporary array that you need to you merge it to, and then you have to copy it back. Okay. You don't need to do that with the other sorters. You can do all of them in place, so they don't take an extra array. And so quick sorter, insert sorter, select sorter, and heap sorter. They're all just concrete sorters that use the abstract sorter. So here in figure 4.7 is the code for the abstract sorter. So let's check this out. So class A sorter, void sort. All right, and here we have, so let's take a look at the parameters. A is the array, low is the low index, and high is the high index. And the precondition is that 0 is less than or equal to low, and high is less than the capacity of the array. Are we good? And then the postcondition is that what? A low dot dot high is sorted. Are you with me? Okay. And then what does split do? Split, what's the precondition for split? What has to be true for split? Low has to be greater than, low has to be less than high. So here's low and here's high. That means there has to be at least how many elements in order to do a split? There has to be at least 2. The smallest one you can have is 2. So it can be anywhere, are you with me? It requires there to be at least 2. Because you can't split if there's not at least 2. All right? And then the postcondition is that what?
The midpoint.
The midpoint. Yeah, is between. Now, let's take a look at the parameters. What does this mid do? Do you see low in split is low called by value or called by reference? Here, in split, is low called by value or called by reference? Called by value. So the actual parameter will not change. Is high called by value or called by reference? By value. But what about mid? That's called by reference, because what's the job of split to do? It has to compute what the mid is, and it has to change it for the calling program, for the calling function. Does everybody see that? Are we good? And then what about join? Join also has the array and low and mid and high. But this time, mid is what? Call by value, because the job of join is not to change mid. It's given mid, and it's to join them. Is everybody clear on that? And one more thing I want to point out. What is the type of the array A? It is a what? It's a reference to a what? What is that? Well, up there in sort, when it says A, what is the type of A? A seek. You remember that? What is that? That's our old what? That's our what? That's our safe array. Remember how we did the safe arrays? So now all these things we're using there. Okay, we're going to be reusing all of this stuff as we go along. Is everybody clear? So it's a safe array. So if you write some algorithms with this, and you get an array out of, you try to go outside the array, what's going to happen? You're going to get an error message, and it's going to say boom, boom, boom. It's not going to let you do it. And are you with me? And so now here in figure 4.7, you guys, is sort. And notice that it is defined in the abstract class. It is implemented in the abstract class. Look what it does. Look what it does. Given the array A and low and high, what does it do? It says, well, we implement the precondition here. And what's the code? If what? If low is less than high. Now what if low is not less than high? What does it do? Nothing. Because if low isn't less than high, we either have one or none. We've either crossed over, or we have either one or none. And if there's one or none, there's nothing to do. And we're good. It's sorted. It is sorted if there's one or none. Because one element is, by itself is sorted. Are you with me? Okay. But if low is less than high, then what happens? We have a local variable called what? Mid. And then what do? We split A, low, mid, high, and mid's going to be called by reference. So what is split going to do? It's going to change the value of mid. Are you with me? And then what's it going to do? Sort A between low and what? Mid minus 1. So there's the one recursive sort. And then what's it going to do? Sort A between mid and high. And then what's it going to do? Join A, low, mid, high. And there it is. You don't have to write this. It's done once. When you do the merge sort, you don't have to write this at all. It's just done this once. And so this is doing this. Does everybody see how that works? It's a common mistake for students to want to do that when they do the merge sort, because you think, oh, I got to do, but no, that's done. Is all you got to do is implement two things. Actually, just one, because one of them is trivial. It's just the split and the join, because the sort is already done for you. I think we're going to skip over this material so that we can get to about the preconditions and postconditions, so that we can get to the actual code that you're going to need to complete to finish the merge sort. So just one more comment about how the main program uses a sorter. So the question is, so you have this system all set up, and you want to, say, write a program that does a sort using this template method pattern. Here's the way you do it. First of all, you have an object called a sorter. All right? And it is an A sorter is the name of the class, the abstract sorter. Okay? And so that's a pointer to an abstract sorter. And then what you do is you say sorter gets new, quick sorter int. So now here's the question. After we do sorter gets new, quick sorter int, so that int is the actual parameter of the C++ template. So now we are sorting integers, right? My question is, what is the type of, trick question, what is the type of sorter? Is sorter an abstract sorter, or is it a quick sorter? Trick question. Well, it was a trick question, so there's not one answer. Remember how abstraction works? Remember how abstraction works?
I know where you're going. I'm just like trying to
Try to remember what the terminology.
It's different from when it executes. It's different.
Yes, when it executes, it's different from when it compiles. Now, which one was called what? When it compiles, that's called what? Static or dynamic?
Dynamic.
Oh, you had a 50-50 chance. Okay, now look, you guys. Let's remember this. This is all. We're going to be doing this over and over and over again. So, static is at what time? Compile time. Dynamic is at what time? Run time. And so the static type is this type that's determined when it's compiled. Right? And so when it's compiled, so its static type is A sorter. Its dynamic type would be quick sorter. So we don't know in the code whether this, sorter could be new merge sorter, or it could be new heap sorter, or it could be new, you see what I'm saying? That sorter could be anything. But it's determined at run, its dynamic type is determined when you do new. But you could new it with anyone. Does everybody see how that worked? So that's a good review there. Okay? And then you would have to do something like, you would have an array T. So now we have the sorter, now we need the array. So you'd have declare an array T, which is one of our safe arrays, and you'd prompt enter the capacity, etc. And now that you have the sorter and the array, the actual code to do the sort, and then you would also know what the length was, depending on whether you got it from a file or whatever. And then the way you would actually execute the sort is you would say, so sorter is this object that has a public sort method. And you would say sorter.sort, and you would give it your array, and y is 0, length minus 1, because that's what? Low and high. Does everybody see? So that's how you would use it. So you've got two objects going on here. You've got the safe array and you've got the sorter. So that's how you would use it. So now let's go through let's see what you have to do to code up the merge sort for your assignment that's due on Tuesday. What do we have on that first line is template class T. What do we have on that second line? Class merge sorter. What's that colon?
Oh, it inherits.
Inheritance. That's inheritance. So what are we saying? Merge sorter is a what? Subclass of what? A sorter. Are you with me? So there's the UML diagram, merge sort, inherited from, are we good? Merge, yeah. So merge sorter inherits from A sorter. And here's that temp A. Remember we said that there's a temporary array A that you can use to copy back. All right, or you use the temporary array to merge, you merge into the temporary array and then you have to copy it back. All right? And now we have split. So we have, now what is, split and join are protected. Now in C++, what does protected mean? So we have public, protected, and private.
So is protected, it can only be accessed within its class?
Yeah, within a class or subclass, right. And private means only this class can access it. An object of this class can, but public means anyone can access it. So these aren't for the general public, the split and the join, right? They're just they are to be used internally. And here, now you remember this C++ 11 thing, override? Remember remember why we need that? Or why we want to have that? That's because we are telling the compiler that we are overriding from the superclass so that it can give us a meaningful error message. All right. So here now, in this next slide of figure 4.9, I've done the split for you. It was very easy. Look what it does. Remember mid? Look here. Mid is called by what? In split, mid is called by what?
Reference.
It's called by reference, right? Because when the abstract sorter implemented sort, it assumed that it was going to be set, right? So look. So what does it do? It just says mid gets what? Low plus I plus 1 divided by 2. So does everybody see what we're saying? If you're sorting between 20 and 40, right? So if you have an array here and and it's between 20 and 40, then 20 plus 40 is?
60.
Divided by 60 plus 1 is what?
61.
61 divided by 2. Now that's integer division is what? 30, right. And so 30 is the midpoint. Right? So that's all it is. That's all that does. And then your exercise, so don't touch any other code. Is all you have to do is what?
Join.
Join. So how do you do join? Okay, so how do you do join? We'll go through a little some snapshots here. So here's the way merge sorter works. Now this is at the high level. We're looking at this from the point of view of the A sorter, the abstract sorter. So let's suppose that the initial list is 90, 20, 80, 50, 40, 10, 95, 60, 30, 70. And we want to sort between 0 and 9. So that's the initial list. Then what happens is, if we do the split, now let's do the calculation for this split. If we do the calculation for the split, what's 0 plus 9 plus 1 divided by 2? 9, 10, right, 5. Right? And so that means that it's divided into two sublists from 0 to 4 because when did it sort? From 0 to mid minus 1 and then from mid to, it sorted from low to what? Mid minus 1. Are you with me? So here, it sorts recursively from low to mid minus 1. Are you with me? And then it sorts recursively from mid to high. Are you with me? And then it does what? Join. And as a result of doing the join, it does this. But now you see, what you have to do is all you have to do is implement the join. All right, so now here's what you have to do. All you have to do is write one loop. Please do not write more than one loop. Because look. So here's how you do the loop. What we do is you should have one loop on K. And K will go from what to what?
0 to 9.
Yeah, 0 to 9 in this case, but not in general. From what to what?
Oh,
Not 0. Not 0.
points like the
I to j minus 1?
No. From low to high. It'll go from low to high. It will go from low, because the parameters are low and high, and low and mid and high. So it will go from low to high. Is everybody clear? It'll go from low to high. Right? And that's the only loop you need. Okay? And what you should do is, if I is greater than or equal to mid, what do you know?
And you're at the end of it.
You're at the end of the first one, and you can just automatically bring the second one down. Else, if j is greater than or equal to what? Or is greater than what?
High.
High, you know that what?
You're at the end.
You're at this end, and you can just automatically do what? Bring the other one down. Else, what do you know? Else you know that you're somewhere in the middle and you have two things to compare. Are you with me?
Yes.
So in this case, we have two things to compare. So what do we compare? A sub what? I and A sub j. And which one is smaller? I sub j. Okay, so you move this down, right? And k is always just the control loop, the control variable of your single loop should just be k. Does everybody see? And here, sorry. And now what happens is j is at 30, right? So now what do we compare? The 20 and the 30. And which one's smaller? This was not a hard question. 20 and 30, which one is smaller? 20, so the 20 comes down, etc., until you get to the end. All right? And then the last thing you have to do is copy them back. So what you should do is you should use that underscore temp A is this one on the bottom. And that's already set up. Don't try to, I have allocated it for you in the code. Don't make your own array, okay? So, are we good? So, okay, does everybody see how to do that? And then we'll do some analysis on this on Monday. But I think this should be good to get you started on your homework assignment for Tuesday. Yes.
For the homework assignment for today.
Oh yes. Oh, would you like us to talk about that for a second? All right. What was the algorithm? Maybe I can bring it up. This one. This one.
Yes.
Int sum gets 0 for int j gets 0, j less than length, j plus sum plus gets a sub j. Oh yeah. So here's 0. This is 0, and this is L minus 1, right? And this is like 5, 8, 7, 3, 20, 15, 22, blah, 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 blah. And what is this loop doing? It's int sum gets 0. All right, so sum gets 0, right? And then what happens is each time you go through the loop, what happens? J, so here, if J is here, each time we go through the loop, if J is here, what is the value of sum if J is here? What is the value of sum if J is here? There's a 0, 1, 2, 3, 4. What is the value of sum if J is here?
20.
Is it 13 or is it 20?
20.
Well, for part of the time it's 13.
Well, that's see, the question is, it's after J has incremented and before it does the test. It's after it's incremented, but before it has gone.
Before it was
Oh,
Are you with me?
yes. 13.
So what is the value of sum here? 13. All right. And if J is here, what is the value of sum? 20. So what's the invariant?
Sum is
Sum, not as greater. What's the invariant? Sum,
is less than.
no, is equal to what? What is sum equal to here? 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 What is it in general? It's equal to the what?
A0.
It's equal to the what?
So
It's not for all, it's equal to the what?
the O summation
It's equal to the sum.
of I.
Now can you figure it out?
The post condition is also in summation.
Yes, because you want it to be, what do you want it to be?
The sum of them.
Yeah. Okay, is that good? Yes. Yeah, that was a good, I'm glad you asked me that. Actually, we'll keep this on the recording, even though I kept you over. Thanks for, yeah. Is everybody, are we all good? Yeah, you know, that was a really good question. And the reason I assigned this is because it took me a long time to figure out, to be able to spot to be able to recognize what a loop invariant was when I was first learning this stuff. And I know it can be elusive, but you just have to do it a few times. The more you do it, pretty soon you'll be able to see. But being able to recognize what the loop invariant is helps you to write the loop correctly in the first place.
And the loop invariant has to be true before you even go into it, right?
Yes, so in this case what happens is int sum gets 0 makes the invariant true
But if the
when J is 0.
when J is 0, isn't that A sub 0, so isn't it? Oh, but then it's the one before.
Yeah, yes. Yeah, you see how that? And then empty range rule. Da-da.